Okay. Okay. Let's see. Very interesting. Oh, there's Mike. Yeah, I've swapped one of these PLLs in. 145, 151 in place of the yes. Yes. Experiments. So I whacked this guy up real quick, like you know, with copper board and obviously some ferric chloride, and now I'm just trying to work out, you know, what it does some interesting stuff that I would not have expected it to do. It works, though. It does work. I'm just programming it by hand. But the block diagram of this just seems interesting to me because, you know, we've got, let's see. Where's the thing that I was looking at here? That's that page. This page. It's this page right here. We've got this pin 21 thing here, and it's rather stumping me because transmit receive offset adder. This input controls the offset added to the data provided the input and inputs. This is normally used for offsetting the VCO frequency by amount equal to the IF frequency of the transceiver. This offset is fixed at 856 when the TR is low and gives no offset when it's high. A pull-up resistor ensures no connection will appear as a logic 1. Okay, so it has a you know, it's pulled high by default. Okay. I pulled it low, and you know, I could get the PLL to sort of do something. You know, like lock, for example. Like right now, it's locked, and it's on. In fact, it's on channel 25. And I've got no pins programmed. All pins are high, because, well, they all are all internally pulled up. So all of the divider pins are pulled high. So you know, that would be equal to a since they're all pulled high, that would be equal to a division of whatever the max should be, whatever the max is, which would be 16,383, which is rather curious. So now, if I just grab a tweezer and go from the ground plane to a pin say, let's go to a least or a most significant bit, like pin 11, and I just sort of ground that out. That puts the radio on. Where does it put the radio on? See if I can get a hold of the pin properly. Like, it actually makes no difference, which is very peculiar. So how come that makes no difference? I mean, I just pulled a most significant bit low, and it made no difference. So what gives? You know, that makes no sense. So I pull a most significant bit low, it makes no difference. Hello, hello, hello. I'm wondering if, okay. Wait, it is making a difference. It's not making that big of a difference. Well, that's actually very curious now, isn't it? And that actually might make some sense. Because it's capable of such large divisions, this could, in theory, because, I mean, you take a 145, 106, or whatever, you know, it's 8-bit, 9 bits. You know, this thing is 14 bits. So we have a lot more resolution on this. So if I pull a most significant bit down, or N0 on this, the radio goes from 27235 to 27233. So 2 kilohertz? That's crazy. That's very interesting too. Just 2 kilohertz. Huh. Okay. This has different, this is definitely working differently. Huh. That's really crazy. They're definitely going to have to experiment with this PLL more. I don't know. I really don't know. So, it's the first page. Pin descriptions, frequency, reference address inputs. That's RA 0 through 2. Actually, those are floating. N counter program. These provide a data input to divide by N counter when it reaches the count of 0. N0 is the least significant. Oh, it's backwards. Oh, no wonder it's having such a little effect. That's the least significant bit that I'm toggling. It helps to read the bloody data sheet. Okay, so now if I go to the most significant bit then, which will be N13, which will be pin 23, I should have a drastic change if I shunt that to ground. So 23, see 28, 27, 26, 25, 24, 23. So if I just tweezer 23 to ground, goes out of lock because it's moving it too far, which I kind of would have expected. So let's try 10 or 11 for grins. So that should not shift it quite so drastically. Still too drastic. Still too drastic. So how about 9? 2, 3, 6. It loses it there. Okay, that one took me to 26.91. So, no, it doesn't. That took me to 26.91, and when I let it float, goes to 25. So, that's rather curious. Huh? Oh, I'm guessing you can set 5 kilohertz steps. Yeah, I kind of alluded to that. You know, in the data sheet here. I actually, the reason I was having a little bit of trouble with it before is because I didn't actually realize that they had, that they've got this sort of backwards, you know, as far as most significant, least significant bits. So I was toggling the least significant bits, wondering why it was changing it so little. So, what's interesting about this is that I still don't understand what this transmit thing is, because I have a typical application here. Receive and transmit adds 856 to the n value. I'm kind of stumped as to what the actual divider is at right now. It's all good. It works. It is working. It's just doing something rather... I guess I'm probably... offset is fixed at 856. I mean, this transmit receive line that adds 856, it just seems like a very specific... That just seems like a very specific value. So, you know, I'm kind of like, you know, what is the significance of the 856? It's not jumping out at me immediately. And 0 is least significant, and the 13 is most significant. And they are all pulled up to a high state. So basically everything is high. So since everything is high, I get my calculator. That's what it seems to be here. Let me just see what the current current value is. So it would be so all 14 bits are ones. So the encode value is 16,383 plus 856, which seems ridiculous to me. So I must be completely misunderstanding, you know, what's going on here. So let me just write this value down. Because if all inputs are pulled high, so that's going to be one, whoopsie, get this back, 16383 plus 856. Come on, calculator. The Windows calculator is so screwed up. I mean, it doesn't seem to work. 16383 plus. Why am I having such a hard time with a bloody calculator on Windows? Frickin' Windows. 856. Or 17239. I could have just added it up on the paper bloody faster. Jeez, Pete. So that seems like a crazy. Now there's these other things, the reference divider, which I've got all set high. So where's the chart for those? Divider value 8,192. So what happens when I pull one of those down? Because that's one thing that I'm not really too clear about, the reference divider. So that's 5, 6, and 7. Let's just pull one of them down. Oh yeah, that made a difference. Because it put it at 30 megahertz. Okay, so I got to work out the... I didn't think that that was something that I had to work out. I guess let me look at the block diagram of this damn thing. All else fails, look at the bloody block diagram of this chip. Alright, oscillator 10.24, 14 bit divide by R, 14 by 8 ROM reference decoder. So we've got a table in ROM that sets a 14-bit divider. Of course, I'm just going to have to work out what the correct. So when I just pulled 6 low, 6 is RA1. So that went to from 8192 to 256. Yeah, I see that now, which is why I was getting some funky results. Because I just put this bloody radio in 30 megahertz just by toggling one of the reference inputs. You know, and that obviously, you know, really it made it move. Let me tell you. All right, so I made this board to sort of accept, you know, bodgery. So I'm going to have to do some bodging, but it works. So it's just a matter of figuring out how it works. Since I have never worked with this before. So I built this little board based on the okay. Bytes referenced by an RA setting rooms yet. Okay. I just got to figure out the right combination. So that's all. So let me get some bodges in place. So I'm guessing to try setting RA2 to a 1 for a nice divide by 1024 and give that a grin. So RA2 is pin 7. So, wire's a little thin, but it'll work. Come on. There we go. Let's ground this bodge wire and get our 1024. Okay. RA2 high only. You're right. I got it backwards, don't I? You're right. I got it backwards. So I want to leave that, and I want to bodge the other two together. So I'm just going to cheat, and I'm just going to bridge those two pins and ground those two out to pull those low. So there we go. Yeah, I got it. Okay, so that's what I've got now. So that's going to, of course, put the radio out of lock. So where did we end up? Let's give this thing a tweak and see if we can find it. There we go. 2607. Alrighty. So we're down bottom of 26 megahertz. Now, what I'm wondering about is if I can remove this TR thing that I had that grounded out, because that was adding something to the PLL. See, now it's, yeah. So I guess I still need that. I don't understand why I need that. That's what I'm kind of not understanding. Why do I need to ground out that transmit receive offset adder? Still. I guess I still need more. Right, it's going to divide by an additional 856. So I need an additional 856. So, yeah. The problem is everything's pulled off. It does add 856. That's the whole thing. That must mean that I still have the reference dividers. The RA 0 through 2 must still be wrong, because it works when I add the additional 856 in both cases. So I can't add any more to it because I have no inputs in this at all. So it's actually at max right now, which would be the 16 some odd thousand. So where did I write that? 16,383. So let me just make sure. I'll put that back. Come on. And of course I've got to retweak it. There we go. Incredibly small lock range. I'll tell you what's interesting about this is that that's what I was going to do next. Is that this is allowing this radio to work down in low 26 megahertz. So what is it doing to the with the PLL that the 145-106 can't seem to work out? Wow, that's really, really, really slow. No, that's lock detect. Duh, I knew that. Okay, so I'm measuring lock detect. It's mostly happy, but it's erratic. It's just too low. It's fluttering. All right. It can be stable though. I don't know. Anyway, so I need the two 0 and 1 high, which means I need to take 2 low, and 2 is pin 7, which is actually what I had to begin with that I didn't want. So take this wire out, take my bridge out. Okay. Put this wire back on pin 7. All right. Let's give that a go. Of course, it's not locked again. See where if we can get to wherever it ended up. I can't. Okay. So since I can't get to where it ended up, I can't get where it ended up. So let me try it without this, because this may actually now change things. No, nada. So what I probably need to do is find a least significant bit now. Let's see, which would be like 13 or one of those, and try to ground one of these guys out. It's where I need Mike's foot pedal. Okay. Let's give it a tweak. See if we can find it. No. So, why not? Okay. Nope. Next bit down. Let's give this a go. Nope. So I'm guessing that just took it too far away. That just took it too far away. It works when they were all high. When they were all high and I was adding, so RA1 and RA2, tossed 1 watt. all the RA1 through 2 are by default pull-up resistors. So if they're left floating, they're actually pulled up internally. So if I pull these two guys, I bridge these two pins, that would be 2410. So let's see. Can we find it? No. Nada. Oh. Just have to get one off eBay. Sure as hell would work right now. Okay, so I'm in a state where now nothing is working. So let me remove this wire. That should be in a state that it was. There we go. So that's back to channel 25. I'll tell you what, this is a funny, interesting PLL chip. (14-bit R counter), so it only works. It didn't work when I had, let's see, 6 and 7, RA1 and 2 high. That didn't work. That was 2410. 2048 would be RA1, which would be 6. This is a PLL that's typically used in VHF type of equipment, or I found some references to this being used in cellular telephones. So it's typically, it would never be used in CBs. I don't think, at least none that I've heard of. Pull N0 low. Yeah, I guess you could use it in a scanner. Try that. Of course, there we go. Where are we now? We're down to 26 megahertz again. So let's try 0. 0 is 11. Let's give it a go. It's gonna tweeze it to ground. It changes it by like a few hundred hertz. I mean, yeah, I mean, it changes it by like a few, yeah, a few hundred hertz. Yeah, huge amounts of channel possibilities is right. The radio will never do it. It's really just, this is just totally tinkering. I mean, this is nothing all, this all this is. I don't believe this is locked. Seems to be drifting around. I don't think this is really locked. No. This is just, yeah. Um, let's see. Well, I'm using the phase detector B output. I mean, I could try to use well, no, that would be the one you would want. You would want detector A, because if it's leading, it goes negative. If it's lagging, it goes positive. So, and that's what you would need with this VCO. Because that's exactly how it works with the 8719, and that is exactly how it works with the 145-106, which does work in this. It's working. It's just that I'm trying to I'm at a loss as far as what this divider is doing. This reference divider seems to be the ticket to all of these issues of the woes here, but you know, which one is the right one? I probably should have wired up all of the dividers to dip switches or something. I just figured I would bodge the thing in here and see what happened. Well, yeah, this